Good morning. This lecture is about equality constraint in the terminal state. So we are going to consider problems in which you impose the terminal state. And the conditions are, as you can see in the top of the slide. So you want to maximize your costs subject to, sorry, this is a misprint. This should be an equal sign. So the state equation, x dot equal to f of x in u. The initial condition x of 0 equal to some specified vector x index 0. And now we have an extra condition, which is the terminal state. So you are imposing the terminal state, x of capital T equal to some specified value x index t. And during the interval of optimization, you impose that the control takes values in a set of admissible control values capital U. So what is the modification of Pontryagin principle? The main modification is that now you have an extra condition, which is the terminal condition, and you lose the terminal condition on the pseudo state, on the adjoint, on the solution of the adjoint equation, the cost state. So you have your state, cost state, and optimal control along an optimal trajectory satisfy this triplet, satisfies the state equation, the initial condition, the terminal condition for the state, the fact that U belongs to the set of admissible states, and the adjoint equation. Furthermore, at each time, the Hamiltonian is maximum with respect to U. So this is very simple, although, of course, we have to provide some examples to work, to be able to work with this new version of the principle. And the issue is that if you solve this equation, the adjoint equation, the equation for lambda, then the solution depends on constants. So what you have to do is to carry up these constants, and in the end you end up with your control depending on some constants that are related to the fact that you are not imposing conditions on the cost state at some point. Now, after you get the optimal control parameterized by these constants, you impose the initial and terminal conditions, and you solve the state equation using the optimal control. And by imposing these conditions, you can compute these constants and solve the ambiguity in the manipulated variable. I guess that in abstract terms, in cold blood, I could say, this looks very difficult, but let's see two examples to illustrate this procedure. You can find several examples in my book in chapter 12. So the first example is very simple. Suppose that you have 2 points in a plane. This point with coordinates A, and another point with coordinates small b and capital B. And you want to move a curve, you want to find a curve that links these 2 points. And this curve is such that the length of the curve is minimum, okay? So at this moment, you are saying, well, the solution is obvious. Okay, in a sense, it is obvious. You are probably saying it's a straight line. Now, let me ask you, what is a straight line? Can some of you tell me what is a straight line?
Has no curvature.
Has no curvature. And what is curvature?
Change of derivative. I don't know.
Okay.
Well, like in a mathematical way, it can be described as a change of derivatives, but in a geometrical approach, it's similar to, I don't know, a
So a
circle.
straight line for you is something with a constant derivative. Okay, that's a good answer. That's a good
If
answer.
it's a,
I accept
but
that answer.
if it's the circle, it's 1 over the radius, the curvature.
Yeah, yeah,
If it,
but
yeah, sure. Go ahead.
I don't know. I was just saying, like, in terms of a geometric view. Yeah, of course, it's not like it doesn't have a radius, a fixed radius, but I think that's the simplest curvature possible. I think I can think of.
Okay, so one important notion is curvature. And if it is a circle, the curvature is the inverse of the radius. If it's not a circle, you can think of an osculating circle. That is to say, a circle that is tangent to the curve, and that defines the curvature. But perhaps a better way of describing a straight line, well, the story of the derivative, it's perfectly okay for me. Another way is you say that in a plane, a straight line is something that if you deviate from the straight line, you increase the distance between the 2 points. But then we have to be able to compute this minimum length solution. So one possibility is to apply Pontryagin principle. Now, I have a J, which is actually the expression that you have studied in the basic course on calculus for the length of a function, of the graph of a function. So it's the integral of the square root of 1 plus the square of the derivative. I'm considering smooth curves, so curves that have derivative everywhere. Otherwise, the story is different. Now, so we have this expression for the length, and we have this problem, finding the curve with the minimum length. How can I transform this into an optimal control problem or into a control problem? Can you have any ideas? You need a state equation that relates the state x with the control.
I think the control can be the derivative.
The control can be the derivative, yes. Actually, we saw one example, well, the very first example that we saw on applying Pontryagin principle. I used that trick to transform a geometrical problem into a control problem. So we define a state equation. The state is the position, and the state equation is just dx dt equal to u. And in this way, I'm able to transform my cost into a standard form, because originally the cost was depending on the derivative of the function, and the Lagrangian function should not depend on the derivative. But since u is equal to x naught, then you can write it as the square root of 1 plus u squared. And in this way, this is a valid Lagrangian to apply the theory that we have, the theory that is to say Pontryagin principle. So the problem that we have to solve is to minimize the cost given by this expression, the integral of the square root of 1 plus u squared, subject to what? The dynamics, which is x dot equal to u, the initial condition on the state, x of small a equal to capital A, and the terminal condition, x of small b equal to capital B. So let's apply the previous principle. And I've repeated here the formulation of the problem. So we have a Lagrangian which is minus the square root of 1 plus u squared. So the gradient of L with respect to X is just 0 because L does not explicitly depend on X. F is equal to U, so f of X is 0 because F does not explicitly depend on X. And if you write the adjoint equation written here in the general case for this special case, well, f of X is 0, L of X is 0, so lambda dot is just 0, lambda is a constant. But you can't say which constant it is at this moment because you don't have any terminal condition for lambda. You lost the terminal condition for lambda. So what do? You have to compute your optimal control as a function of lambda and then solve the state equation with this optimal control and impose the initial and terminal conditions. So let's do this. The Hamiltonian is lambda transposed f. F is u. L is minus the square root of 1 plus u squared. So your Hamiltonian is lambda u minus square root of 1 plus u squared. Now, if you study this function as a function of u, you will find that this function has a minimum or a maximum in this case. And so you compute, to find this extrema, you compute the derivative of h with respect to u and you equate it to 0. So just apply the ordinary rules for derivative to differentiate this with respect to u. And you know that lambda is a constant. So basically, since lambda is a constant, what this formula tells you is that u is a constant. Of course, you can solve it with respect to u, but the important fact is that u is constant. So if u is constant, remember that u is the slope of the curve. According to your theory, the theory of one of you, I can't remember the name, the solution must be a straight line. Now, which straight line? Because you have many straight lines. To find which straight line it must be, or better to say, the value of u, which we know now it's constant, we apply the boundary conditions. So we apply the fact that x of a is a and x of b is capital B. So pick up your model, and now you know that u is constant. So you can solve this equation. It's very simple. You just integrate, and if you integrate by the fundamental theorem of calculus, the integral of x dot is x minus x of a, and this is, so xt is x of a plus the integral of u. U is constant, so this is just u times t minus a. Now, apply the terminal condition, and the terminal condition tells you that for t equal to small b, x of t is capital B. So you get this expression that you can solve for u, and you get the optimal control, that is to say the slope of the curve, which is b minus a divided by small b minus small a. And if you look again here, you are just dividing the difference between the ordinate of this point minus the difference of this point, so this segment up to here, and you are dividing this by this length here between b and a, okay, to compute the slope of the straight line that that drives the curve from this point to that point. Okay, this was a very simple problem, but it illustrates the technique. So you lose conditions to find the pseudostate, but you still have conditions on the state. So you have to carry on these constants on the pseudostate up to the end, solve the state equation, with the optimal u, and then apply the terminal conditions to find what these constants are. So let's solve a more interesting problem, and for which the solution is by no means obvious. So suppose that you have a one-dimensional robot, that is to say, a robot that moves along one direction, that I call the position of the robot along this direction x1, and I call x2 the velocity. So x1 dot is equal to x2, and x2 dot is the acceleration. It's the velocity, is the force on the robot divided by the mass. So this is a kind of manipulated variable, of normalized manipulated variable. And my robot is in one state given by 1, 1. That is to say, it's at position 1 with instantaneous velocity 1. And I want that after 1 unit of time, my robot becomes also at position 1, but with velocity 0. It can evolve between different states. And I want to transfer the state of the robot from this state. Sorry, this should be x1. There is a typo here. x1, I want to transfer the state from x1, x0 to x1, while minimizing the energy. The energy is the integral of the squared force. Okay, so the problem is minimize this integral, which is the energy, while transferring the state from an initial value to a final value which is imposed. So in this case, the f function of the state equation is x2 and u. And if you compute the Jacobian matrix, you get this. So this is the f1, the x1. f1 is x2, this is 0. This is the f1, the x2. So x2 differentiated with respect to x2, partial derivative, is 1, and so on. These two other terms are the f2 dx1 and the f2 dx2. The f2 that does not depend on x, on any of the x's, so it's 0. And the Lagrangian is minus 1/2 of u squared. Be aware that I've written the cost like this, but I want to minimize it. So I put a minus here, and instead of minimizing, I'm maximizing. That's a trick that you can do. So my Lagrangian is minus 1/2 u squared. Now, to compute Lx, I have to compute the partial derivatives of L with respect to x1 and x2, but L does not depend on x1, neither on x2. So these two derivatives are 0. And the adjoint equation is minus lambda dot equal to lambda transposed fx plus Lx. So minus lambda dot equals to lambda transposed, minus lambda dot transposed equals to lambda transposed fx plus 0, which is the Lx. And now I can break these equations, this matrix equation, into two equations separately, and I get lambda 1 dot equal to 0 and lambda 2 dot equal to minus lambda 1. So this means that lambda 1 has a 0 derivative, so lambda 1 is a constant. Let's call it C1. Now plug C1 in the equation for lambda 2, and if the derivative is a constant, then a constant C1, then the function is minus C1, because we have this minus sign here, C1t, and plus some other constants. So lambda 1 and lambda 2 are given by these expressions, and we don't have any condition to compute C1 and C2. let's look now at the optimal control. Let's look now at the optimal control. So I write the Hamiltonian, lambda transposed F plus L. So remember that it's lambda 1 F1, which is X2, plus lambda 2 F2, which is U. And L is minus 1/2 of U squared. So this is just a definition of the Hamiltonian. And as you can see, this is a concave function. It's a parabola turned upside down. So to find the maximum of the Hamiltonian, I just differentiate and equate to 0. This term does not depend explicitly on U, so the partial derivative is 0. And this term is linear in U, so the partial derivative is lambda 2. And the partial derivative of this term is just minus 1/2 times 2 times U, which is minus U. So the optimal control verifies this condition that this derivative is 0 for lambda 2 an optimal pass. But we know that lambda 2 is C2 minus C1t. So we can restrict the possible values of the optimal control. So the optimal control will be a straight line, and we have to find out this C1 and C2. So how can we find C1 and C2? We plug it in the state equations. So x2 dot is U, so use the optimal value for U. And now integrate. If you integrate x2 dot, you get it x2 dot of t minus x2 dot of 0 equals to this integral. And now compute the integral between 0 and t of C2 is nothing more than C2t. And the integral of 0 and t of C1 sigma with a minus sign is sigma 1 C1 sigma squared divided by 2 computed between 0 and t, which gives you minus 1/2 C1 t squared. So using results that are pretty standard from calculus. Now, once you have the velocity, you can also integrate it again to get the position. That's the other state equation. So if you integrate it again, you know that they are related by this expression, and now plug the expression for x2 that you have obtained, and you have to integrate this term. Let's do it. So the primitive of 1 is t, the primitive of C2 sigma is sigma squared divided by 2 times C2 times 1/2. And then you have the primitive of sigma squared, which is sigma cubed divided by 3. So 1 divided by 3 times 1 divided by 1 gives this 1 divided by 6. So we have expressions for x1 and x2. And now you impose t equal to 1. And if you impose t equal to 1, you will get this expression for t equal to 1. And let's go back. Also this expression for t equal to 1. And you want x2 to be 0 and x1 to be 1. So this gives you this set of algebraic equations for C1 and C2. And you can easily solve it, and you get C1 equals to -6 and C2 equal to -4. And at this point, you have solved the problem because you just replace C1 and C2 in the expressions for the optimal control. And you know that the optimal control is 6t minus 4. Now, you can replace this value of the optimal control in the state. And you get these expressions for the optimal state. Here it's a simulation in which you see here the evolution of u in time. So this is u as a function of time, the optimal u as a function of time. And in this graph, you see x1 as a function of time, here x2 as a function of time, and here is the state space. So you start here and you do this movement up to this last point, just to verify that with this control function, you meet the specification of going to 0, which you actually do. So these problems are always solved like this with more trouble and less trouble. You can find more examples in the previous exams and tests, and also in my book where things are better organized. Any question? Okay, so I would like to add a number or one important property for the Hamiltonian, and for that to introduce that property, I'm going to write the state and cos state equations in a different way, the so-called Hamilton form. So remember that the Hamiltonian is lambda transpose F plus L. And the adjoint equation has this expression. So it's minus lambda dot transpose equal to lambda transpose Fx plus Lx. Now, if you compute the partial derivative of the Hamiltonian with respect to lambda, well, it's just F, because this term does not depend explicitly on lambda, and this term is linear, the first term is linear in lambda. So this is just F, but F is nothing more than x dot. So you have this first equation, which is the state equation can be written as x naught equal to partial derivative of the Hamiltonian with respect to lambda. Now, if you compute the partial derivative of the Hamiltonian with respect to x, then what you get, look at the definition of the Hamiltonian. You get lambda, which does not explicitly depend on x. And then you have a function that depends on x and u. So the partial derivative with respect to x is just lambda transposed and f differentiated with respect to x partial derivatives, plus the partial derivative of L with respect to x. But this here, if you remember, if you look at the joint equation, is nothing more than minus lambda dot transposed. So you can write that lambda dot transposed is minus the partial derivative of h with respect to x. So this set of equations that have some symmetry, because one gives you the derivative of x with respect to time as a partial derivative of the Hamiltonian with respect to the cos state, and this gives you the derivative of the cos state with respect to the partial derivative of the Hamiltonian with respect to the state. This is the so-called Hamilton form of the state and the joint equation. So these two equations are equivalent to the state and to the joint equation. Now, consider a situation in which the optimal control values are always inside in the interior of the set U. That is to say, you never have bang-bang solutions. So if this optimum is inside the set of admissible values for U, this means that the condition of extremum is just that the derivative of h with respect to u is 0. So this rules out situations in which you have a switching of the optimal control. This was what was happening, for instance, in the robot case that we considered before. Now, in this case, the condition of optimal is dH du equal to 0. But I stress that this only happens in situations in which the Hamiltonian is a concave function with respect to u. So we say, think of it as a parabola, not always a parabola, but something, a cup turned down, which is differentiable. So these three equations define the optimum. Now let's use these three equations to prove a property for the Hamiltonian. Suppose so that we have time invariant dynamics, as we always have. So this means that the state equation does not explicitly depend on time. It's just x dot equal to f of x and u, does not explicitly depend on time. And also the Lagrangian function is has no explicit dependence on time. Then we are going to prove that the Hamiltonian is constant in time. Let's do it. It's very easy. So compute the total derivative of the Hamiltonian with respect to time. So the Hamiltonian depends on lambda, on x and u. So you have to compute the partial derivative of h with respect to lambda and multiply it by lambda dot, plus the partial derivative of h with respect to x multiplied by x dot, plus the partial derivative of h with respect to u and with respect to u. Okay? Of course, there should be a u dot here that I have not included. It's a typo. Now, what happens is that this term dh d lambda is x dot, and dh dx is minus lambda dot transpose. So these terms cancel out. Okay, these two terms cancel out because you have x dot times lambda and x dot transpose times lambda transpose and lambda dot transpose times x dot. And this term also vanishes. It is multiplied by u dot, but u dot exists. It does not go to infinity. And dh du is 0 because of the optimality condition, this last optimality condition. So all these terms vanish, and the total derivative along an optimal path, the total derivative of the Hamiltonian with respect to time is always 0. Now, we have proved this for situations in which u is differentiable with respect to time. But it happens that this property is true when you have a piecewise constant u. So if you have a bang-bang controller, then h will also be constant. The proof is much more complicated. It's completely outside the scope of this course, but it still holds true. Okay? So even in the case where your control is bang bang, the Hamiltonian will be constant throughout all of the optimization interval. Let's see two examples. The first example is something that we have already considered. It was one of the first examples that we considered. It was a mobile robot, the famous 2 double integrator. So x1 position, you differentiate it, you get the velocity. Derivative of the velocity is the force. And then I want to maximize the distance traveled during the optimization interval minus the if u is the rate of fuel, is the force. If u is the force in this case, then the square of the force is the is the power, and the integral is the energy that you consume in the maneuver. So you want to travel as much as you want, but at the same time, minimizing the energy that you are consuming. This was a problem that we have solved. And here you have the expression for the Hamiltonian, which is a quadratic function, and in U, and lambda 1, lambda 2, and the optimal control, which was capital T, the length of the optimization interval, minus current time T. Now, you can compute with this value of U, you can solve the equations to find x1 and x2, and you find that the Hamiltonian is actually 1/2 of the last time instance times the square. So the Hamiltonian is constant. So if you plug x1, the optimal value for x1, the optimal value for x2 given from these expressions by just integrating the state equations with the optimal control, you plug it here. You also plug the values for lambda 1 and lambda 2, and you plug the value for the optimal U, and you get a constant, okay, which is in agreement with what I said. If you want to have a picture, so you have the space U and H, that's a plane. And then you have time, that's the third axis. And when time moves, you have this function of H as depending on U is changing. And this straight line here is our optimal control. Remember that the optimal control was, where is it? Here. The optimal control is capital T minus T. So it's this straight line here. So what happens is that at each time instant, the relationship between H and U is a parabola turned upside down. If you look here, you see that it is a parabola upside down. That is changing because lambda 1 and lambda 2 are changing. But as a function of U, H is a parabola upside down. So when time changes, you have different parabolas, but the vertex of the parabola is over the optimal control and defines a constant line. So you are always having along the optimal trajectory for U, and of course for X and lambda, because it's X and lambda that define the Hamiltonian, you have a constant value. So this is one example. The general proof for this case in which U is differentiable is what we have done. Now, suppose that we have a different case that we have already also considered. We replace the cost by the so-called minimum fuel cost, in which I want to maximize the distance that I have traveled minus the integral of the rate of consumption of fuel. So this is the total fuel consumption. And now I have my Hamiltonian is a linear function of U. So remember that in this case, I must impose, for the problem to be well behaved, I must impose bounds on the possible values for U. So I'm assuming that U is between 0 and some U bar. So U bar is the maximum value that you can take. And so this results on a linear Hamiltonian. And again, and there is a switch on U in this case. The solution is bang bang. I don't have everything here, not to obnubilate your view of the slide, but you can go back to the example that we have solved in the beginning of Pontryagin principal study, and you can compute. You have two intervals, one before the switch of u, and the other after the switch. Remember that u switches from the maximum value to the zero. And in each of these intervals, u always verifies this, takes this value along an optimal trajectory. So it's u bar times t minus 1. So the Hamiltonian is also constant. Although this case we have not proved in the general case, but in this case it's very simple to prove. So what happens? What happens is that in this case, the Hamiltonian is a straight line. So look, for instance, for t equal to 0. The Hamiltonian starts at the origin and goes up to the vertex here. Okay? And so when time progresses, the Hamiltonian is always this straight line. And the maximum of this straight line between u equal to 0 and u equal to u bar is here, is the maximum. So your control is up to some switching instant, also here. And the Hamiltonian along this value for u and for the optimal x and the optimal lambda is given by this straight line here. Now, what happens is that you reach a point in which this point was depending on the relation of lambda with respect to 1 or to t, I think, t, capital T. Then you do a switch, that is to say, the Hamiltonian as a function of u that was this line becomes with a different slope, a different sign and slope. So the maximum is no longer attained for this value of u, but it's for that value of u over there. And the Hamiltonian is that one, but the value of the Hamiltonian is also at the same point. Okay? And you can prove this with your computations, because you can compute the Hamiltonian in this segment along the optimal trajectory, and also the Hamiltonian along in this segment for the second interval. So again, we have the Hamiltonian. So you have to look from this side, okay, to see just a straight line in projection in the plane HT. So this is an important property of the Hamiltonian for time invariant problems. Remember, it's for time invariant problems, which are the problems that we are going mostly to consider. Although the principle is also, the Pontryagin principle is also valid for time varying problems. And two things that I would like to add is, suppose that your terminal time is made free to vary. In that case, you are imposing, having an extra variable. So t is no longer fixed, it's a variable with respect to which you have to find the optimal. And you need an extra condition, and the extra condition is the Hamiltonian at the terminal state is 0. Now, if the Hamiltonian is constant, and since the Hamiltonian is constant, when you have time-varying systems, the Hamiltonian is always 0 at all the points. And you can use this to compute the optimal value of t. So this concludes the lecture for today.